In the last clip, we saw a central atom molecule MO diagram, therefore CO2. But we also saw the very interesting result that if we are mixing two orbitals of different energy, so here there are two orbitals of different energy, the new bonding orbital will look more like the initial low energy orbital and it's going down, and the new anti-bonding orbital will look more like the higher energy orbital and going up. So the initial low energy one goes down to make the bond, the high energy one goes up to make the anti-bond. And we're going to explore this further and we're going to look at this system right here. We're going to look at the system OF+. Okay, so we need the energies of the orbitals, and so here we know that the energy of the 2s from last time is minus 32 EVs, and oxygen 2p is minus 15 EVs. Do we expect the fluorine orbitals to be higher or lower in energy? Put it in chat. And we expect them to be lower in energy because fluorine is more electronegative. Fluorine 2s indeed is minus 40 EVs, and fluorine 2p is minus 18 EVs. And we're going to put the oxygen on the left. We'll treat that as the central atom, and the fluorine will be on the right. So let's just draw those orbitals. Here there are the three oxygen orbitals, 2p orbitals, the px, py, and pz. And then here I'll put the oxygen 2s. Even lower in energy on this side, this is the oxygen side. I'll put the fluorine over here, and here is the fluorine lower in energy. There's the 2s at minus 40 EVs, and I'll put the 2p's here. Okay, so that's the energy scale. And now we need to start mixing orbitals. We mix orbitals that are close in energy that make good interaction. So pick a pair. You can choose sigma, pi, you want to have the best constructive interference, and you can pick a sigma p, or you can choose s, best constructive interference close in energy. Take a look at the energies, put in chat which you pick. Yeah, the minus 15 and minus 18 EVs, those are close in energy, and we were going to look at the sigma interaction. And now we get to the crux. The fluorine sigma p orbital is lower in energy. The resultant mixture, the bond, is it going to look more like the fluorine orbital or the oxygen orbital? Put it in chat. Will the resultant bonding orbital look more like fluorine or oxygen? And the answer is it will look more like fluorine. So I'm going to draw it right here. It's more like fluorine. I'll make the fluorine contribution big and the oxygen contribution while bonding small. It looks more like the fluorine orbital. There it is going down. I should also draw the one going up. The high energy one, the anti-bonding one, should it look like more like oxygen or fluorine? Put it in chat. The higher energy one looks more like the original high energy one. It'll look like oxygen. And should I draw? And so I'll draw the fluorine orbital smaller because it's less contribution and out of phase. What should we look at next? Pi or 2s? And remember, what does fluorine not do very well? It doesn't make pi bonds. So this should be a no-brainer. We should pick, I think, 2s because the pi bonds will be very weak. The low energy one will look more like fluorine or oxygen, 2s. Put it in chat. More like fluorine. And the high energy one, I'll go to the oxygen, go up a bit, will look more like oxygen, and it's anti-bonding. And finally, we have to look at the pi interaction. Although the pi bond, there are pi interactions, we know they're very weak. So when I make the pi interactions, should it go down a lot or just very little? Fluorine doesn't make good pi bonds. Should go down just a little. So I'll take the fluorine and it's just going to look a little, and that means it's going to look a lot like fluorine because it's mixing very little. So I'll mix the two here, and then I'm going to have just a very little amount. Oh, where's my color? Just a tiny amount of, barely a bond. And here's the other one. Yeah, probably not a bond. And then we can do this thing. This will look more like the oxygen, barely going up from the original oxygen energy. I make the fluorine very small. Oops, there's a mistake there. Let me correct that. Because it is out of phase. And now I've drawn all the orbitals. This one is, OF plus has 12 valence electrons, 2, 4, 6, 8, 10, 11. By Hund's rule, where does the last electron go? It goes over here, parallel spin, that's Hund's rule. And now, this one is sigma what? Sigma bonding. Oh, sorry. That's not the nomenclature we did. We did it like this. Sigma S bonding. This is sigma S star for antibonding. This is sigma P bonding. And these two, what are we going to call them? Pi bonding, non-bonding, or antibonding? Remember, fluorine really doesn't make good interactions, pi interactions. And so this answer is we should call them pi non-bonding. Here's another pair of pi non-bonding, but these are oxygen located, and finally comes a sigma P star. Okay, sigma bond order. Sigma bond order is 1 bonding, 1 antibonding, 2 bonding. Net 1 bond sigma bond order is 1. Pi bond order. Pi bond order is, well, they're all non-bonds, 0. And we have, therefore, we're going to put the oxygen and fluorine. We know there's a single bond. And we now have to put 5 lone pairs. And which atom is going to get most of the lone pairs? Which is the more electronegative atom? It will be the fluorine. So we will end up with the fluorine is getting 3 of the lone pairs, oxygen 2. And you actually can see a bit of that because notice that the unfilled orbitals are mainly on oxygen. See, these are the unfilled orbitals up here. They're mainly on oxygen. And that's, if one more pair of electrons went there, they would go on to the oxygen side. And so it's oxygen plus. Good. That's the MO diagram. Oh, did we do paramagnetism or diamagnetism? Is the system paramagnetic or diamagnetic? It is. It has unpaired electrons. It is paramagnetic. Okay, so that's the last clip. And there's the one figure MO diagram. And these are online, and you can watch these recordings again. But I believe with practice, you'll get quite good at MO diagrams.